Hi everyone. So in our last class, we studied the ground state of the Heisenberg Hamiltonian for two different cases of the coupling constant, positive and negative, right? So in the situation that the coupling constant is negative, J, we saw that the ground state, as expected, should be ferromagnetic, meaning the localized spins can all or should all point in the same direction. Good. So by now you know that in any system, a given quantum system, if we have a certain ground state at zero temperature, then in general it will have some excitations as well once we disturb the system. And the idea is, just as the ground state is a signature of a given Hamiltonian, its excitation is also a signature because different Hamiltonians will have different kinds of excitations. So then let us go in that spirit and apply that idea to our ground state of the Heisenberg Hamiltonian. So let's start with the ferromagnetic case. Okay, so what are the kind of excitations that one should expect in such a ground state? So this is what my ground state looks like. All my spins are aligned at different sites, right? And then let's say this is the jth site where the SZ is perfectly polarized, so it's equal to S. Now, what does physically exciting something means? So what it essentially means is that I'm going to try to flip one of these spins. Now, if it is S equals half, there are only two options, so I can only have it up or down. But in general, if I have a large spin system or any general spin, not just half, then in general there will be 2s plus 1 orientation. So I can just simply change it. So I can lower it a little bit at the jth site. Now the question that we are interested in, this is the same question, for example, we have hit again and again. For example, in a phonon, the lattice is perfectly ordered, all the ions at the lattice points, and then I disturb a little bit. Similarly, in electron gas, when we did plasmons, electron gas is perfectly in a ground state, and then we disturb a little bit. So there are always options. That disturbance can propagate as a wave throughout the system, and then it becomes a collective mode, or it could just die down at some, I disturb it somewhere, and then it doesn't really propagate, it dies down within a few lattice points. So here we are trying to, taking the same idea as in plasmons and phonons, we also want to find the similar kind of mode that acts as a traveling wave, and that will essentially be what is called a spin wave. And as is usually the case, just as sound wave and everything, we can then quantize it, and the quantized version of such a wave is called magnons. Okay. So like phonons, we expect magnons to be described by bosonic operators, which means whatever the creation and annihilation operators of these new quasiparticles are, they should follow this boson algebra. Okay, so now comes a little bit of a mess. Not a mess, but you have to be very careful here. Conceptually, there is a little bit of interesting aspect that one needs to consider. And what is it? You see, in reality, this operator Sj minus is the actual operator which is lowering the spin. So this is the one that is really creating the excitations. Right? So then one would expect that this operator which is lowering the spin should be related to creating an excitation, a boson excitation, a magnon, which is at the same site. I'm doing A dagger, where A is this operator. Now straight away I cannot just equate the two. And why not? Because to begin with, this S operator, if I'm in the real spin space, it can only work 2s times. Right? It can just keep on. So for example, S equals half, I can only operate it 2 times half, 1 times, because immediately it will switch to minus half. And then if you try to operate it anymore, it will give you 0 because you cannot lower it anymore. Similarly, if S is, let's say, 5 halves or anything, essentially there are 2s plus 1 orientations, and therefore this can operate 2s times at most. Now, if I add the meaning that each time I'm lowering it by 1 unit, I'm creating 1 excitation particle, that means that there has to be inbuilt in the mechanism, in the algebra of this, the information that this can only operate finite times. You see what I'm trying to say? So this can operate finite times because this is the real physical spin. But the excitation that I'm creating, I want to behave as a boson particle, but I know that if I just use the standard boson algebra, then I can have indefinite number of particles created at the same site, right? Because that's what the commutation relations tell me, right? Unlike fermions, it does not put any upper bound or constraint on the number of particles that you can create at a given quantum number, which here is J. So then although the meaning is this, we somehow need to do a proper definition so that these two are connected along with these properties inbuilt. And this is done by what is called a Holstein-Primakov transformation. Again, goes after the people who invented it. So this is again a canonical transformation, and we know what canonical transformation is, which is I am mapping one operator to another such that on the right hand side this operator has a certain algebra and this operator has a certain algebra, and those algebras should be maintained. So then the challenge is I need to associate S with A in a way such that A should follow its own bosonic algebra, S should follow its own spin algebra, but I should also have the constraint that this should totally give me finite number of creations and annihilations. Now this particular transformation, you can easily check that it actually satisfies the canonical condition, which means if A is the standard bosonic commutation relation, it follows that, then you can automatically prove that these will follow the spin algebra. Just a simple algebra, so you can show it. So it does satisfy that. But it also gives us the much needed constraint, which is it automatically restricts the number of excitations. Why? You can easily see that each time so let's take this one for example. I know each time I'm lowering, I'm creating one bosonic operator. Now this expression, the prefactor, the factor here with attached to this, you see this is going to give you the number of bosonic excitations created. Now one time you create, this will create it, and then the next time when you are creating again, this will be 1, 2 and so on and so forth. So by the time you go to the lowest one possible, the 2s plus 1th orientation, which is the lowest orientation of spin, completely opposite, this AJ dagger AJ will give you 2s because you have already created 2s times disturbance. Now the moment you put 2s here, you see 2s over 2s gives you 1 and 1 minus 1 0, so it automatically stops this ladder process. Okay, so that's the essential trick. So that is the only trick that one should know, and as you can see, it's very ingenious. That is the only thing that is new in this part. Once you have done this, now the rest of the thing is simply algebra. Okay, so the plan is now obvious. Now that you have gone through superconductivity and interacting electron gas, now you know exactly what we need to do. So what do we need to do? We know a Hamiltonian. So we are just going to write this in terms of A and A dagger. So what will we get once we do that? Remember our superconductivity. These are the quasi-particles, excitation quasi-particles, like we had gamma 1 and gamma 2 operators in superconductivity. So if you plug that in the original Hamiltonian, just as we had done in the HBCS, we will get what? A sum of terms of one of which will be ground state energy, which will be independent of these operators, meaning that's not the part which comes from excitation. Plus there will be a term which gives you the excitation energy, which is actually dependent on these operators, right? Exactly what we had earlier in our superconductivity case. Also, because we are looking for traveling wave solutions, spin wave, we will definitely go to the Fourier space. So what are you going to do? This full Hamiltonian Si.Sj, we'll write it as z component, and xy will write it as plus and minus. We'll express all these three terms in terms of the Ai dagger and Aj dagger, Ai and Aj. And then we are just going to write the Fourier decomposition of these A's, so that we go to the K space, and then obviously we're going to find H in terms of these, automatically giving us the excitation spectrum. Cool. So essentially, from the physics point of view, you now know everything. So honestly, the rest of the thing is just algebra. I can just stop here, and you, in principle, if you do this diligently, you should be able to recover everything. So it's tedious, that is true. I mean, it will take a little bit of time to work through it. So I have gone through most of it, but there are some missing steps. I urge you to go through it. You should do it once in its entirety, so that you know exactly what are the pitfalls that can happen in these kind of calculations. Okay, so please do go through it and fill the missing steps. Okay, so basically just you have two kind of terms, SZ, S plus and S minus. We first need to write it in terms of A and A dagger, and then we will Fourier transform. Okay, so let's start with SZ. So let's start with SZ square, because that's easy to write it in terms of S square and S plus S minus. So this we are writing only in the jth side, so everyone is on J, and then we just use the definitions in terms of A's. Okay, then multiply everything, algebra, 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 we end up with the following expression for SZ square in terms of A's, which means this is the expression. And now you see the initial intuition that had helped us build the transformation, it indeed holds, because you see the spin, the Z component of the spin at any site J is indeed the total spin minus how many number of excitations you have created, right? Perfectly makes sense. Okay, so number of bosons is precisely the number of times spin has been stepped down at a given site. Next, go to the Fourier. So I'm just using exactly the notations of the book, but as you understand, L here just stands for the number of sites. So it need not be one dimensional, okay? It can be any dimension. So if this J was continuous, as we had done before, we would write 1 over root V, and because J is discrete here, we should write 1 over root N, and N being the total number of sites. So they are just using L here. Okay, next step is, unlike in the Z part, S plus S minus together, because S plus has this half, clearly this is, it's trickier to handle these. So in general, it's of course not possible to do this. So what one can do is one can make some approximation, which is assume that the number of excitations created over the actual spin, meaning the number of times you have stepped it down, is much less than 1. That is, we are in a system where the spin is large and we are just creating a little bit of fluctuation. Okay, this is what the condition means. You can easily understand why we are assuming this, because the moment we assume this, we can easily just do a binomial here and just truncate this series. So this part is not necessary, it's just convenient to do this calculation. Otherwise, you just have to keep going higher and higher. Okay, good. So once you have done that, you plug it into S plus, that A, and then in the place of A, you just plug in the form of the Fourier. That's why, as you had 3A operators, you will have 3B operators with the appropriate exponential term here. Okay, that's it. Similarly, Sj minus can also be found, very similar expression, and Sj of Z is also, as we had found out earlier, it was bilinear in A already, so this is also bilinear in B dagger with the appropriate coefficient. Good. So now essentially we have Sjz, Sj plus and Sj minus in terms of these new operators B and B dagger. So the next step is just take these expressions and plug it in here. Now while plugging it in, you will essentially get what? You will get 3 kinds of terms. One term will have no such dependence on B and B dagger. That will give you the ground state energy. One term will be quadratic in B, B dagger B, this kind of thing. That we call, let's say, H naught. And then there will be higher order terms, B dagger, B, B, and so on and so forth, right? So what do these expressions mean? Ground state energy is ground state energy. We have already found this before in last class, but as you will see, and as expected, this will automatically give you this energy as well. And it should match our previous expression, this expression, and it will, as you will see. This is the part we want to find, right? Because remember, what is quasi-particle excitation? It is essentially a term that gives you the number of particles which are created. So it should be quadratic in the B operators, and it should come as B dagger B. number operator. So these are the number of magnons, and this is what we want to find. Any term which is quartic or higher orders in these operators, just as we had written down electron-electron interaction term, this essentially means that it is a term which embodies magnon-magnon interaction. So you can see how very similar this is. Okay, this was our kinetic energy part of electrons. This is our sort of electron-electron interaction term. Okay, so this is not something that we are interested at the moment, so we can neglect this. Okay, but in general, if you want to go beyond this kind of thing, then people will do these kind of calculations. They have to go beyond and include this. Good. So because we are interested in H0, let's calculate H0. So the first, the S term, the Z term, right? So the Z term is essentially Siz and Sjz. Now Ij, remember, these are all nearest neighbor interactions that we have considered. That means J, so this I is essentially, I can just write it as J plus delta, where delta is the vector that is connecting the jth site to the nearest neighbor. Of course, this, so throughout I just skipped the vector sign everywhere, but as you understand, all of these are vectors at the end of the day. So I will skip it in most of the cases, but you should understand. Now the choice of delta vector is of course dependent on dimension as well as the lattice geometry. So in one dimension it is just plus and minus in the direction of the chain. In two dimension, if it is a square lattice, it will be these 4 nearest neighbors at 90 degrees. If it is something else, hexagon, let's say, then it will be 3 nearest neighbors and so on and so forth. So those are the essential vectors, that essentially the vectors that you need to include here in this term. Okay, so Si we had, Sz we had already calculated before this. So we just calculate, plug in the expressions for them, except that here it is for J and here it is for J plus delta. And then now we have to multiply the two. Now you see, as we had anticipated, there is one term S square which has no operator in it. Clearly that is the ground state energy contribution. There will be two terms, this times this and this times this, which will be quadratic in the B operators. That is what we are looking for. That is your H0 part. And there will be some terms which is this times this, which is quadratic, which is these magnon-magnon interactions, which we are not interested. So you just take these two terms, cross terms, you will get that. Then as usual, summation over J, because we have a summation over J here, that will obviously give us delta function in K1, K2. So finally you can reduce this and get the following expression, which is already in the number form, Bk dagger Bk with some prefactor, right? You remember this looks exactly like the kinetic energy term of electron gas. Next, we have to calculate the part where it is S plus S minus Ji, again replacing I with J plus delta and summing over all delta. You can, again, I'm skipping steps here, fill this part in. Z here again is the number of neighboring sites, and Gk here is essentially the structure factor, which is properly normalized, which is 1 over Z times e to the power I k dot delta, where you have summed over all the nearest neighbor vectors. Similarly, the other term, the third term, which is Sg minus, which is Sj minus Sj plus delta plus, same calculation, you will get the following. Okay, good. So now we have everything that we need. Collect all the terms. The first term, as we expected, will give you the ground state, and this, if you can go back to the earlier lecture last week, you will see that it exactly matches what we had before last time. And then you have the term which is H0, which is bilinear in B operators with this prefactor. And then you have other terms which we have neglected here. Okay, so we have 3 terms which is quadratic in B, and we need to properly now put it in a form so that they all look like B dagger B, number operator. That's very easy. You just use proper commutation relations to change anything that is B dagger into B dagger B, and that's what I have done. And then you, whatever is remaining, you just have it at the end. Now you see, this is a constant. This has no operator dependence. So this is some constant. And you can argue this just goes into the constant ground state energy. But we have already seen that the ground state energy that we calculated has already matched the one that we had last lecture. That means this constant is actually 0. And this is obvious if you take this summation. Why is this 0? Because what is this? This is just e to the power I k dot delta summation over all k. And we know what this expression is, right? This summation is non-zero only if delta is 0, right? E to the power I k dot r, remember, if we sum over r or k, the other variable has to be 0. It's a delta function. But then delta cannot be 0 because by definition delta is the vector which connects the nearest neighbor, right? So it cannot be onto itself. That means delta is not 0, which means this term is always 0, so that can be kicked out. So this then is our general expression. This is the number operator of the excitations, and this is the total kinetic, the total quasi-particle energy that needs to be now calculated in under different circumstances. So this is our general formula. Good. Now we can end here in principle, but one can make some more progress if you want. For example, if you assume a situation where this gk is g minus k. This is not general, but it is a particular situation where such things can happen. And what does this mean? What it essentially means is that we are thinking of something which has inversion symmetry. For example, a square lattice, right? One particular lattice, if it has a neighbor at a given vector delta, there is also a nearest neighbor at minus delta. So this is what we mean by inversion symmetry. So if that is true, which is of course not general, then this even simplifies more because these two becomes equal. I can pull the 2 out, and this is exactly what I get. So now I can simply write this as summation over k times some energy wk, some dispersion, times the number operator, where this omega k is essentially this. So this is precisely the energy spectrum of an excitation in a ferromagnetic case. So let's see what this looks like in certain scenarios. So of course, as I said, it will depend on the dimension and the lattice geometry. So for example, if I think of a linear chain, one-dimensional lattice, then for any atom there are two neighbors, plus delta, plus minus ai, I being this direction and a being the lattice spacing. Then if I just plug this in here, you see that gk just becomes cos times ka, right? So then I can just plug it in and then I'll get my expression. Now, having said that, there is something else that we should understand, which is the long wavelength limit. So you should be able to understand, map this very well to our tight binding model, which is in the electron case. Remember, in the electron case, we also end up with, when we have tight binding models, we end up with an energy spectrum whose dispersion is essentially given by similar terms, right? You have to sum over nearest neighbor and you get certain Ek, right? Remember, in a tight binding lattice, you get minus T1 minus cos K and something like this. And then while doing tight binding, I had also mentioned that there is something called the long wavelength limit or the low energy limit, which means I go to the limit where this K goes to 0, small wavelength. So in that case, the expression will become quite general. It does not really matter that much on the geometry. In general, it can, but in general it shouldn't. And this is the reason why, because we can just expand this guy here. So we still have inversion because otherwise we won't be able to arrive at gk equals g minus k. But other than that, let's say we go to small k without actually thinking about the particular lattice geometry. Just expand this. So I get 1 plus x squared over 2 as usually is obtained. Now this again, because it's a centrosymmetric inversion symmetry, when I sum over delta, this will go to 0. So I have 1 minus this. So therefore omega k, which is this 1 minus gk, will simply give us proportional to this thing, which is ks squared. Clear? So now you see what we have achieved. So what this tells us is that a ferromagnetic excitation spectrum, if I want to excite a ground state of a ferromagnet, the way the energy goes with momentum of the collective motion of the system, the spin wave, its dispersion relation is quadratic in K to begin with, just as you would expect in the electronic case. And more importantly, there is no gap. Okay, so this is very similar to what we have in case of electrons, for example, right? Not the kind we had in superconductivity, where we had a gap here. Okay, now next lecture we will do the antiferromagnetic case, where you will see that this will change a little bit. So this quadratic will becoming linear, and again you won't have any gap. Now all these have some meaning, in particular the gap. Why there is no gap? There is a reason for that. Even without doing all these calculations, one could have predicted that, and we will discuss it very briefly next lecture. Okay. All right, so that's all for today. I'll see you guys in a couple of days. Okay. All right, bye.